Hello, everyone. Thank you very much for being here. Good afternoon. My name is Blanca Tovar. I'm going to be the chairman of this session, BIO1. We are going to start with our first presentation. Is called Trustworthiness and Interpretability in Deep Learning for Cardiac Ultrasound and presents Tarek Bergaut.
Thank you so much for. First of all, I would like to thank you, all of you, the CCE organizers, for this great event. I'm trying to contribute every single year in this excellent conference. Thank you very much for making this great event achievable. First of all, I'm going to present myself. My name is Tarek Bergout from Algeria. I work in University of Batna too. I have a position of chief laboratory technician, and also in my free time I do my research, which is generally is about artificial intelligence, meaning using artificial intelligence technique in several fields. I've started firstly working on predictive maintenance. Then I passed to many fields like cybersecurity and material science and engineering, and thereafter I ended up working on bioinformatics. My contribution that I'm going to present today is about trustworthiness and interpretability in deep learning for cardiac illness, meaning that we study uncertainty quantification and real-time explainability during the training process itself of deep learning algorithms when trying to concentrate on segmentation of cardiac images. So what we are going to see in this week is that investigating of uncertainty quantification in deep learning models, as well as interpretability. And the idea of this paper is not using interpretability or explainability as in traditional works which is post-processing the prediction. This paper will focus on using interpretability in real-time training process, meaning that we allow the model to as much as possible to reach explainable predictions during the training process and as well as generalization process on unseen samples. Also, we'll discuss about using deep learning networks with a lightweight size, such as the convolutional network with minimal features and layers. Also, this paper will discuss the use of Bayesian optimization for hyperparameter tuning in kind of fair comparative analysis between different types of or variants of this proposed convolutional network, including, of course, the basic one. And then we just want to mention in this case that we are using this database of about 500 pages. We use two phases. We have about 2,000 images in this case to analyze and to study. By the way, this abbreviation of CAMOS is a project means that it's the cardiac acquisition and for multi-structure ultrasound segmentation, which is a very famous data set in this case, and a benchmark that we can use it to compare algorithms with the state-of-the-art methods. Of course, after analysis, we proved that the philosophy of trust or uncertainty, including uncertainty and interpretability in deep learning, can improve accuracy and also clinical applicability of the model, because the results are achieved through both uncertainty quantification and real-time interpretability. So this here is an example of our used database. Let's zoom in here. These are different images from different phases and views of the heart obtained by ultrasound images. And the second row here of this figure represents the ground truth labels obtained by or defined by experts in the field, maybe doctors or well-specialized radiologists in this field also. So what we can see here is that the ground truth and the area also outside the ground truth have some similarities in colors. So the deep learning model will of course misinterpret these areas and make mistakes. For example, when trying to segment or detect a count of the area of the ground truth, will of course make mistakes by also highlighting areas outside of the ground truth. And the challenge here is we try to make our deep learning model as much as possible tries to surround only the ground truth by improving it and concentrating on many areas on the images. So after explaining this challenge, we move now to explain our methodology that we have used in this work. The first step is data acquisition. We extract samples from the database of CAMOS here, and in the processing stage, we use only one step, which includes normalizing the dataset. We intentionally use only normalization and assume that both labels and images are perfect in this case. This is the case in general medical databases because we want to concentrate on the algorithmic complexity and the accuracy in this case. So after that, we just resize the images to be in line with our computational environment, meaning our laptop or our personal computers. We resize intentionally, of course, the images to make sure that the computing or the matrix multiplication and the deep learning process of nonlinear abstraction is achievable on ordinary computers. Also, an additional step that we have made here is the background here, which is like the area outside this triangle here. We have removed it manually using a specific mask to prevent our algorithm to take the prediction process of the area of ultrasound images with that background, just to avoid computational mistakes. Now, the design model here is an artificial learning algorithm based on convolutional neural network, which is very famous and used generally in image processing, of course. We use a convolutional network with minimal features, meaning a layer or two only, with the Bayesian optimization for hyperparameter tuning and the loss function that includes here, as indicated here, uncertainty quantification features, which is basically the confidence interval of a 95% confidence level. And also the thing that makes this study special is this interpretability stage. We use kind of reverse artificial neural network, so the network based on lighter algorithm that is depend on pseudo inverse of the matrix. The goal here is to map the hidden layer, the output hidden layer of the deep network directly to the output to measure the quality of reconstruction. And the question is why we did this. We did this to make sure that the data set one passes, or images one passes to the multiple layers or nonlinear abstraction of the deep learning does not vanish and still have meaning of the realistic meaningfulness of the realistic database. So reducing the error of reconstruction in the objective function or in the loss function, meaning increasing interpretability and increasing or providing explainable predictions as much as possible. So the next step is the prediction, of course, computing some metrics of the simulation process, and also both visually and numerically. Let's pass now to provide some samples from our results. In this figure here, we show the original image, ultrasound image in specific view, for example, two-chamber view. And here we see the ground truth defined by experts. In this case, we use 3 algorithms. The basic convolutional neural network as a reference, of course, to improve or to measure how much the percentage of improvement of our proposed method. We use also a CNN, a convolutional neural network, only that depends on uncertainty quantification. And finally, our proposed algorithm, which we termed UAE CNN, means uncertainty convolutional neural network. We see mistakes that made by a basic deep network by drawing a counter on area outside of the completely outside the ultrasound picture. And also, we see some kind of improvements here in the uncertainty-based convolutional neural network, meaning the uncertainty awareness helps to avoid these mistakes made by basic deep learning. Also, when we observe the UAE CNN, meaning the proposed approach, provides a counter with less intensity and better than the one of uncertainty awareness only. And also, of course, better than the basic CNN. In this case, what we conclude? We conclude that including real-time interpretability and uncertainty awareness helps in providing more interpretable and accurate results, of course. The same thing applies here with a more complex structure of 4 chambers view, where our proposed algorithm also achieves better results than uncertainty-based convolutional neural network and also basic convolutional neural network. And the same conclusion can be provided in this case also, even under increased complexity in hard structure. The curves here showcases to us the prediction errors and confidence intervals. What we can see here in both training and testing phases that the proposed approach, meaning that the one that includes interpretability and uncertainty, shows less fluctuations, better than the uncertainty awareness convolutional neural network, and also the basic convolutional network, which is the 3 figures here in general prove the theory of including interpretability and uncertainty awareness that is very important in hard segmentation so far. Also, the numerical evaluation, without going in details and numbers, confirms the theory. Also, additional tests of statistical tests prove that the results are statistically significant in regards to the previous conclusions. So, to summarize, our work here tries to prove a theory that including uncertainty awareness and interpretability in real time for deep learning for hard segmentation, basically use images is a very important in clinical decision-making process. And in future work, we may be concentrate on additional features in regarding extending the layers of deep learning, maybe using another databases and another tools to further confirm this theory. And thank you very much for your listening to me, and I'm open to any question from your side.
Thank you, Tarek. Thank you for your presentation. Is there any question here in the room? Is there any question online? Okay, I have a question, Tarek. How much does it affect to your segmentation, the quality of the ultrasound images? Did you work with different qualities, or is it only from one equipment and one person, the ultrasounds?
So there are many patients. In this case, I use the data set, as I said, that contains about 500 patients, meaning, and in 4 cases, meaning we have about 2,000 images in this case, what I meant by these explanations, I meant that the dataset is very heterogeneous, contain multiple types of images and multiple cases, and the conclusions in this case are accurate also based on the variability of and diversity of information we found in this data. Also, we can in the future maybe try on other data and obtain more generalized conclusions.
Okay, thank you, Tarek. Thank you very much. I think we can. I have a question. Yes. I would like to know how you can get the data set, like where you can ask for the camps. I think it's an open source database. Tarek, here there is a question about the dataset, but I think Camus is an open source database. Am I right?
Yes, it's an open source dataset that anyone can access. I believe it under open access license, CC BY, meaning you can use it for non-commercial uses only.
Yeah. Okay. Thank you, Tarek. I think we can continue with your second presentation. And I would like to ask you something about your presentation. You have it as but it's not in a presentation mode. Can you make it in a presentation mode, please, so that we can see it bigger because it is not in the whole screen.
I will try it in the presentation mode and let me know if you see it or not. I don't know how to do it in this browser, but I will try to zoom as much as I can.
At the bottom right, but there are 4 arrows pointing to the corners.
I'm not familiar with this browser. So what about now? What about now? Do you see my presentation in full mode? Hello? Is this presented? Can I start presenting my paper?
Correct, please. Yes, please, but you are not sharing. Can you share your presentation, please?
Okay. Now we are moving to next paper, which is about using compressive sensing and certainty-enabled deep learning in cardiac ultrasound images. So this contributes on the same data set that I have presented in the previous work. So what I want to test here is a new theory about compressing the images, because also there is a problem of faced in compressing images in the literature, meaning one of the famous algorithms that's used is JPEG 2000. When we compress our images from the original sensors, of course, we lost some data. So also researchers, what I'm trying to point here is that researchers need to focus also on quality of images even before the training process begins, meaning we consider images are accurate as possible. So this is why I have tested a new theory about using compressed sampling and certainly enabled learning in cardiac ultrasound. So what we are trying to do in this paper is to improve the quality of images based on different specific tools of image compression and quality analysis. This is why we discussed the use of compressed sensing, which is a very, very accurate tool that can take images or take signals from our space to another sparse space where only a few elements can be used in a processing stage and have the same meaningfulness of the original space. Meaning, for example, like in frequency domain, when we use, for example, wavelets or different families of wavelets, we have obtained some specific principal harmonics to be based on them in analyzing information from images. And then we return to ordinary space to obtain and analyze and obtain conclusions and so on. Compressive sensing, I have used it before in different works, and for me, it's a very efficient tool that I have experienced with such kind of magical transformation from full rank matrix to sparse domain, and use only few samples to return based on L1 norm minimization. And also, in this case, we use the same philosophy that we have used in a previous paper, depending on a lightweight convolution neural network based on the resources, computational resources we have here, which is a personal computer only. And also we use Bayesian optimization for hyperparameter tuning. The reason I am using always Bayesian optimization, we have experienced it and used many tools, swarm intelligence tools and genetic algorithms, and they found that Bayesian optimization is one of the best tools in terms of accuracy and speed. So it is accurate, fast, and accurate. This is why I'm concentrating on using Bayesian optimization always in most of my publications. Also, this paper will concentrate on using the theory of confidence intervals to reduce uncertainty, besides to accuracy, optimizing accuracy in the same time. Segmentation, of course. The same database of Camus database is used in this case to discuss these theories of using uncertainty and also compressive sensing in improving images qualities for hard segmentation. So this figure here, as previously discussed, also shows different phases of heart ultrasound heart images, and also the ground truth labels made by experts. The same remarks of previous papers of intensities
sharing and continue, please. Can you hear us? Because we cannot hear you.
Y ahora sí.
We cannot hear you. Hi, Tarek, can you hear us? Technical problem can be solved. And meanwhile, we can continue with presentation number 4. The presentation number 4 is semantic segmentation of skin macule images and is presented by Luis Toribio Campos.
Okay, hello everyone. I am Fernando Campos from Pupitan in IBN, and with the Dr. Alvaro Rio, we will present our work titled Semantic Computation of the key medical images. First, the contents that we are going to talk about in this presentation is at first a bit introduction about our motivations to do this project. Then our methodology that we follow to do this project that include the database, the evolution metrics, and the proposed architecture. Thirdly, we present our results, and finally, we'll give you our conclusions. Well, melanoma is one of the most aggressive type of skin cancer, and an early detection is important to improve the prognosis of the patients with this illness. However, um, a diagnosis based on a visual inspection is subjective, sorry, and depends of the experience of doctors. In that order of ideas, this project is focusing develop an automatic system that can highlight the interest region in order to get morphological characteristics that will help us to an early diagnosis. In this example of maculas, we can see a melanoma and a macula without risk. We can see how one of them is more circular at the contours, and in the interest region, we can see different tonality of colors. Well, our database, we use images from an open source database from web named Kaggle. And this database was separated into classes, benign and malign class. But we didn't use these classes in order to get a classification. We use 500 of class benign and 500 of class malign in order to get a complete database. And then we manually segmentate each original image to get a second binary image that we name mask. We use code in Python where uh, we select point by point the contour of the macula, sorry, and then this code join all the points to get a binary mask. In our evaluation metrics, we use both principal, dice score, and IOU score, or intersection over union. Both metrics measure the similarity between the mask generated by our system and the masks manually generated. Both IOU score focus on the proportion that match with each other, and dice score measure the similarity between size and position. Well, in our proposed architecture, we use an autoencoder structure. When in the encoder part, we have a 5 double inception module, and in the decoder part, 4 convolutional module, 4 double convolutional module. And we use implement a skip connection that connect the output of each double inception module with the input of each double convolutional module. Each inception module has 4 convolutionals in parallel. The first one is a 1 cross 1 convolution. then a 1x1 convolution followed by a 3x3 convolution, then 1x1 2, but we have a 5x5 convolution in the third part, and finally a 3x3 max pooling followed by a 1x1 convolution. And in our each convolutional module, we have a 3x3 convolution followed by a batch normalization block that helps us to normalize the values in the matrix, and activation function like ReLoop that helps us to use negative values in the same matrix. At final of this structure, we have 1x1 convolution to help us to get a binary mask, and we have max pooling in between the double second model in order to get characteristics that will help us to segmentate the image, and convolution transpose in order to get the same size of the original image. With this structure, we have these results. At the top of this slide, we can see the quantitative results. In color blue, DICE score, and in color green, IOU score. We can see a high overlap between predict and ground truth with these results, and we can see too a step of stability. Sorry. This stability told us that there are no overfitting. That is the possibility that the structure memorize the images that we give it. This is important because if this architecture didn't learn how to segmentate and memorize the mask, if we give a new one that didn't have mask, the architecture will working bad. And in the bottom of this slide, we can see the visual results. We can see how the mask generated. Well, we have to say that these images didn't have a manually generated segmentation, but with the structure that we implemented, we get this mask, and we can see that this mask match with the method control and highlight the interpretation. This is a first step in order to get a morphological analysis. And then this loss curve that told us that the model is stable and efficient and converge to 0. We didn't have enough epochs in order to get that the convergence is near to 0, but we can see at the way that the curve is going to work. And in orange color, we have the validation loss that at the same of the first graphics indicate us no overfitting in the epochs. Well, these results confirm the efficiency of the program for image segmentation. Well, in our conclusions, we develop an automatic system that can highlight interest region. This model integrates autoencoder structure with inception models and some blocks like batch normalization and different activation function as linked ReLoop. We get values higher than 85%, 80%, sorry, on the validation set. And these results demonstrate that deep learning can highlight regions of interest for subsequent melanoma analysis. This for future work, we will get some important characteristics to get a diagnosis early of this illness, like the circular of the contour and the color of the color that are inside of this area of in this area. And it is all. Thanks for your attention and interest.
Thank you very much for your presentation. Great review. Is there any person here in the room?
Yeah, I have a question.
Yeah.
In the slides number 9, you present the DICE score and 0.9. That is good or bad? Or what happened with DICE?
Well, the score told us that the segmentation is the manually sorry the
Take it easy.
told us that the segmentation that the architecture do is narrowly that the segmentation that manually that we manually did.
The DICE is a good value because indicates that your segmentation is good. Yeah. And it's very important for you, the segmentation.
It's important because in this interest area, there are some characteristics that we can study in order to get an early diagnosis and help the diagnosis of the doctors.
Thank you.
Some questions. First of all, it looks like a really complete and wonderful project, and I would like to know how you would in the database, if it's something online or you
Yeah.
work with someone.
Well, the database was from an open source Kaggle named Kaggle, and the second database that are the mask that we inherited, we manually segmented it in order to get database to use in the training and validation steps.
And I have one question because I'm not super related, and I would like to know what does represent an epoch? Epoch.
Okay, epoch. Each epoch is how many times these images were presented into the architecture in order to learn important characteristics. And at the best, at the best, no, I don't remember the word. Well, the best experiment of this architecture were with 200 epochs. We did more experiments, like 100 of epochs, but we see that the architecture can learn more.
I have one more question. Once it is ready, your program, how long it takes to run? Is it takes a lot of time or not that much?
Well, it depends of the computer. And in my case, this architecture take around three hours. But But we did another experiment in another computer, and it takes around 10, 11 hours. It depends of the memory RAM and the GPU, the graphic
Processing.
what's it called? Well, the CPU.
Okay, so practically what it analyzes the morphology and the color or the color map.
Yes, the color, but in a future world, we are working to get the difference between the colors of melanoma metal and not risk metal.
It's super great work.
Yeah, because melanoma is dark.
Sometimes it's not the darkness that is a photo or another photo. It's the in not risk metal. There are not a lot of type of colors in the interpretation that in melanoma photo has more different colors inside the interpretation.
The last one. I would like to know if these pictures need to have a recurring characteristic or if internally it gets like a normalization of the color or something.
Sorry, I didn't hear you.
Is if the color it has a normalization or a certain contrast or it make it inside or you put the images with a certain characteristic.
We didn't do a extra step to present these images into the architecture, but in the diagnosis of the doctors, a lot of times they use this characteristic to get an early diagnosis.
Thank you for your questions. Is there any other question in the room? No? Online, is there any question? No? Okay. Thank you very much, Mr. Livia, for your presentation.
Thank you.
And let's see if Tarek is online, please. He's not connected.
Thank
Okay, so let's continue with our big presentation. And is called Classification of Arrhythmic Heart Sounds Signals and is presented by Eduardo Bernal Bonilla.
Hi, my name is Eduardo. I'm a student in Biomedical Engineering at UPITA IPN. And today I'm going to talk about the process that we made for the classification of arrhythmic heart sound signals. I think that it doesn't work. Okay, so first of all, it's important to mention that cardiac diseases are leading because of that in Mexico. Currently, the first approach for detection of cardiac arrhythmias is using the traditional stethoscope. So, if a doctor detects an unusual or abnormal sound during the study, they send the patient for an ECG. When we have the ECG and the PCG synchronized, we can detect with precision the arrhythmia. So in Mexico, it sometimes take a long time. So it consumes valuable time for the doctor and for the patient. In this slide, you can see a roadmap about the procedure that we made for the heart sound classification. I will explain each one, but as an overview, first we have the database development. Then we made a parameter definition. Next, we made the processing database. After that, we process the database, and finally, we use information for the data process for training a neural network. Well, the first issue that we had during the project is that there is a lack of databases about cardiac sounds with arrhythmia. So we need to make our data set with two public databases. One of it is healthy heart sounds from internet, and the arrhythmic heart sounds, we got it from Pascal networks. So when we finish this first data set, we watch an imbalance between the classes because we got more data for healthy heart sounds than arrhythmic heart sounds. So for solve this first issue, we made an ACG and PCG from a healthy patient. This allows us to detect the beginning and the end of each cardiac cycle. So when we watch the signals, we are able to detect that we can segmentate the signal in 2 seconds time windows. That allows us to increase our number of arrhythmic signals. But the issue continues because we still had a difference between the arrhythmic heart sounds and the healthy heart sounds. So we implement a subsampling technique that allows us to decrease the sampling frequency of the original that was 4,000 hertz to 2,000 hertz. That allows us to double our number of signals. And this without adding any artificial sounds or maybe an artifact that doesn't correspond to the natural heart sounds. For healthy heart sounds, we use three different metrics to evaluate the quality of each audio. We use the entropy, the kurtosis, and the SNR. So with these three metrics, we evaluate the quality and select the best audios for the healthy heart sounds. Then that we have our own data set, we use the Fourier transform to obtain a 1 by 1,000 vector of each audio. It allows us to train our neural network. In this slide, you can see the architecture of the neural network that we use. First, we have the input layer. That is the 1 by 1,000 vector that we got in the previous part, that is the process of the database. Then we have 3 hidden layers. Each one has 3 parts. First, we have a dense layer with a relevant activation function. Then we have a batch normalization, and at the end, we have a dropout of the 30%. So at the end, as an output layer, we have a softmax activation that allows us to classify the vectors that we put in the input. Well, now let's look at the results. The results present a high effectiveness because we can see that the training and the value and the validation values increase nearly by 100%. And in the loss graph, we can see that decrease and stabilize nearly to the 10%. That means that our system is learning and there is no overfitting. So the confusion matrix confirmed it in the false negative values. that is nearly to zero, and in the true positive, that is nearly for the 46 values. Here it's important to say that we use the 20% of our dataset audios for the validation part. So as conclusion, the results suggest that the possibility of developing efficient and low-cost computer diagnosis system based on the phonocardiogram records. Such solution may serve as support in clinical practice, and the neural network shows a high effectiveness working with limited data. So this achieved a remarkable training speed thanks to the compact architecture. As a future work, now we are developing a proprietary database in collaboration with the Specialty Hospital of the National Medical Center, La Raza, and various neural network architectures will be explored and evaluated to determine the most effective model. And a clinical research protocol is currently under development to record cardiac sounds from various kinds of arrhythmias. So it allows us to expand and enrich our existing database. So that's all for me. Thanks for your attention.
Thank you very much, Eduardo, for your presentation. And if there is any question here in the room, please.
Yeah, I have a question. In the slide number 8,
Yeah,
you present the artificial neural network, but it's very important that you express that this network is not deep learning
yeah,
and no need convolutional neural network.
no.
This is advantages.
Yeah, it's about the compact network that we use is fully connected. So we can use a small database for training it, and that is why the results that we get are very nice.
So yeah, this is a great point because you don't need a large database.
Yeah,
With a small database, you can train artificial neural network.
yes, that's right.
That is a great point.
Thanks.
I have a question, Eduardo. Why are you using phonocardiography instead of electrocardiography? Usually, arrhythmias, in clinical practice, they use electrocardiography. What would be your proposal? What is the advantage of using phonocardiography?
Okay, talking with the doctors of the National Medical Center, they told us that to use an ECG, they need an space, and a special space to take the study. And added to this, they need 10 derivations study for take the ECG. So when a patient comes in an emergency mode, they don't have the time to connect in a fast way the ECG. That is one part. The other one is that in parts of the city in where there is not a specialist in cardiology, we need to help the people that needs the attention of these cardiac diseases.
Okay, thank you very much. Any other question here in the room? Do we have any question online, please? No? Okay, we have another question here in the room.
How it was that you went to ask to IMS if they can help you in your project? It was difficult.
Yeah, it was too hard because first I need to present the project for an director of one area that is hemodynamic. So then they send me to present the project for the learning directory. So I need to present the project, what are the advantages of the project and what I need from the CMN. So it was too hard, but they accept the project for the part of that we can help people that doesn't have the opportunity of try to solve the cardiac diseases.
And you needed like a paper from the school to show them, or it wasn't necessary?
Sorry, can you repeat the question?
Did you share a document that you are
A student from
student from a visa
Yeah.
or something?
Yeah, I need to present my thesis that I'm developing at Obita. So they saw it and they approved the project.
And for example, to create your database, because you did it, no? How long it took you?
I'm still working on it because the data set that we have is with two public databases, but there is a lack of information about the patients that they record. So that's the weight, maybe the age, the kind of arrhythmia that they had. So I start to do my own database to recollect that information that is important.
That's interesting research.
Thanks.
But if there is no other question here, we can continue. Thank you very much about it. Can you hear us?
Hello? Do you hear me?
Yes, we can hear you. Please share your presentation and we can continue with your second presentation.
Okay, let's continue from here. As I was saying that we have used the same database of CAMOS dataset, and we are trying to prove the theory of compressed sampling and uncertainty awareness in deep learning algorithm. So we have used the general methodology contained using consequently using processing the images same as the previous way, resizing and normalizing and so on. After that, we passed the ultrasound images through compressed sensing and to pass it to a sparse domain to filter them and to improve their quality and return them to original domain. By doing so, some of details will be removed, and then we get a clear, an improved image for next preprocessing. And we continue the same as previous steps, but considering here only the uncertainty awareness, meaning the confidence interval. We didn't include the concept of interpretability in this case. So after testing on the images, we obtained a sample of results. Here, in this case, we have the original image, and in this case, in B, we have the ground truth label by experts. We can clearly see that deep learning have made mistakes by mapping even or by approximating even the background, which has nothing to do with the object that we are trying to segment and locate. Unlike the proposed method that includes compressed sensing and uncertainty quantification shows a smoother counter around the object of interest, meaning the object, the ground truth label by experts. So the results also of uncertainty quantification, meaning the prediction errors by basic convolutional neural networks, and compared to uncertainty aware and the algorithm that involves compressed sampling in the training process achieves better results with less error fluctuation. Only in the testing phase, the generalizability. The errors seems look like the traditional or basic CNN, meaning that the training process is much more improved, but the generalization compared to basic CNN, it's only slightly improved. So what we conclude in this case, that this also confirmed the theory of interpretability of previous paper, but we conclude in this case that compressed sensing has an effect in improving image quality, but also the learning process requires both uncertainty and interpretability to give much more accurate results. So as a conclusion, we started this paper based on a theory that original image that need to be used in building deep learning for medical image segmentation need to be with improved quality. We used compressive sensing to improve the original images, and we studied this contribution in a comparative study, and we proved that compressive sensing has an effect or an impact in improving the quality of images, therefore improving the quality of segmentation. So in the future works, we need to combine this compressed sensing maybe with uncertainty and interpretability and other databases and other algorithms to provide more generalizable conclusion also. And thank you for listening. Thank you so much.
Thank you very much, Tarek, for your presentation. Is there any question here in the room, please? So we have, yes, please.
I would like to know how like in your sentence, how it works the variation optimization.
Did you hear the question, Tarek?
No, I didn't hear it. Can you repeat it for me, or please?
The question here in the room is, how would you summarize the Bayesian technique?
Summarize what? Which technique?
And I don't know, I think this phrase. I don't know how to pronounce. Yeah.
It was the Bayesian.
No.
Yes, I have used Bayesian technique for hyperparameters tuning, and also to include a specific loss function. The loss function term do not include only the classification, the traditional classification terms. So I included the performances, of course, the classification. I don't know how exactly called, maybe complex, something like entropy or something, the loss function, the traditional loss function, and an additional term that contains uncertainty, which means reducing the confidence interval width in this case to improve classification accuracy in general.
Thank you, Tarek.
Thank you so much.
Tarek, I have another question.
Yes.
I can see in your images that there is only one type of view in the ultrasounds. If you work with a different database that has different views, does it still work?
No, this is what I have mentioned in the conclusion as a future perspective. Yes, in this case, despite the fact that the dataset is diverse and contain many patients, many phases, we need to test our algorithm on other datasets to provide more generalizable conclusion, of course, yes.
Much. Do we have any question online, please? Okay. So we finished with this presentation. Thank you very much, Tarek. And we can go to your third presentation, which is a reflective study on deep learning in brain tumor segmentation.
Thank you so much. So you see my presentation here.
Yes.
So my third paper is just a reflective study on deep learning in brain segmentation. So what we mean about reflective study, so this paper do not actually introduce an innovative contribution or something that can have an impact in improving clinical decision making. What we focus on this study is more like a perspective study. We used a deep learning algorithm. We have applied a deep learning algorithm, a traditional one, basic one, which is the convolutional neural network, just to analyze. It's just like a mission of applying and analyzing the result and exposing or disclosing the challenges to readers, because most of the papers recently introduced only, for example, a new idea, and many beginners in the field do not actually understand the basic challenges that we want to solve. So we applied a basic algorithm and we observe the results, and from the results we conclude both conclusions and perspectives for future works and analysis. So what we did here, we used the famous dataset on brain tumors, which is known as a brain tumors segmentation dataset. It is a publicly available dataset, very famous. Many papers have been done based on this open source dataset. The mission is exploring challenges in applying deep learning by both visual observation and numerical evaluation of the algorithms of deep learning. So we focused on practical issues often overlooked in tradition or in contribution in the literature. This is our contribution. Our contribution in this case is basically the analysis and providing a list of perspectives and the challenges faced in this field. So this is an overview of the data set used. The data set depends on many modalities, T-weighted and T1C as seen here in this presentation, and many types. Each type had its own features and characteristics related to colors, intensities, and many features. But during my search in the literature, I found that the T1 type exactly is well used because it achieves more results and more explainable results that can be used in clinical decision making. This is why in this conference paper, on this conference presentation, we focused on this step directly without going through other types of modalities, which is presented here in this figure here. This figure is an example of a brain image provided by magnetic resonance images, meaning the MRI. And there are two labels here by two different experts in the field. These experts could be doctors or radiologists, well-qualified radiologists in this specific field. So there are two labels here. The algorithm, the mission of algorithm of deep learning is to try to approximate this area here, even under these similarities in color intensities in other regions. So after applying our algorithms, the same process of resizing and normalizing images, and also the same process of Bayesian optimization. In this case, why we used Bayesian optimization is not for fair comparison. We used it to make sure that the deep network can reach maximal accuracy under this specific criteria of analysis. So the same segmentation metrics are applied. and we resized the images, the same philosophy, and we used Bayesian optimization and a basic convolutional neural network. This is an example of our obtained results. So we will try in this step here to explain the challenges of deep learning. As we observe here, we have 3 images with 3 ground truth labels in green here. The area in the second row of this figure here, there is a red area. This is the area that is predicted by the deep learning algorithm. What we can see here is there are these deviation of the deep learning model caused by similar color intensities between the tumor cancer and the healthy brain area is very challenging, meaning we found the difficulties. Maybe due to different reasons related to color intensities and similarities in these color intensities in other healthy areas of the brain itself. So numerically, we found even the known architecture of deep learning, the convolutional neural network, cannot achieve accurate results. So we concluded with these challenges and perspective and analysis that the CNN, the algorithms of convolutional neural network have difficult challenges in color intensities. So one need to study and the many areas of the brains, because, for example, the bones and other areas, and how we can get with this concept can rid of them during the training process. Meaning, we try to make the deep learning algorithm focus only on regions of interest during the prediction process. And also, as experienced in the previous presentation of my 2 papers, that uncertainty and interpretability need to be considered in this case to improve trustworthiness, also on the deep learning model. So to sum up, deep learning models in brain tumors detection find challenges in uncertainty, interpretability, and also complexity and heterogeneity of the data set itself. So to improve this, we need to expose our database to improvements in images, maybe compressions and pre-processing, and also in the architecture of the deep learning, for example, testing advanced architecture like transformers, and also and not forgetting the most important thing, which is uncertainty and interpretability. And thank you very much for your presentation, for listening to my presentation. Sorry.
Thank you very much, Tarek, for your presentation. Do we have any questions here?
Yeah.
Yes.
I have a question. But your dice score is very, very small. It's 0.6. It's small.
It is very small. And
Your
what
dice
is
value,
the question here, please?
send the dice score, and it's small.
Yes, and other parameters also are very small, area over union. What I am trying to say here, this is a reflective study, not a contribution in experimental contribution in images. We just used a basic deep neural network on our raw data set that is just normalized. The pre-processing steps are only normalization. The goal of this study is not to improve the accuracy of classification. The goal of this study is to see, just to observe the results and make conclusions and perspectives for beginners, and to find area of research that we want to work on to improve this accuracy. I hope that my answer is clear to you, sir.
But never mention this part, because it's important.
Can you repeat your comment, please?
No, that's all.
Okay, yes, it's okay. But I have a question. You presented this problem about MRI images, but I think it's not only in MRI images. This problem comes in many other types of images. And don't you think that there is also, well, part of this problem comes from the image itself? Not all the equipments have the quality to show the problem. And I mean, maybe the problem is not even observed clearly by clinicians, by experts, either radiologists or neurologists in case of the brain. But there's not only one problem, and it's not only deep learning techniques is the problem. It's many other problems that all together makes this a big problem. What do you think?
Yes, exactly. I agree with you. So we have the equipments that cannot exactly 100% captures the images accurately. And also there is other stages of compressing the images, because a higher level images can be with gigabytes. So we need to compress them using algorithm like the JPEG 2000. After compressing them, definitely we are losing data in these stages. And then it came the resizing of the images, and then the pre-processing, and then training of the deep learning algorithms. I think at each stage, there is kind of loss or vanishing of some important data. And this is exactly what you said. So I agree with you. The problem is not only about the deep learning algorithm. The improvement need to be taken into account in each stage of these stages.
Exactly, yes. Thank you very much, Tarek. Is there any other question here in the room? No? Is there any question online, please? No? Okay, so I think we can continue with, thank you very much, Tarek, for your
Thank you so much.
presentations. Thank you.
Thank you so much.
Okay, we can now go to our last presentation for this session, and it's called Cold Model, Implementation of a Fractional Order Control Scheme for the Estimation of Tau, and is presented by Antonio Del Osa.
Sorry, I am Antonio Loza, but the presenter is Natalia Bravo, my colleague.
Natalia, please go ahead. Natalia, could you present in a presentation mode, please, as a full screen?
Okay.
Okay, it's ready.
Thank you. Good afternoon, everyone. My name is Natalia Bravo. I am with the Laboratorio de Electrónica Aplicada y Biomedicina at the Universidad Nacional de Tierra del Fuego in Argentina. Today, I'll be presenting our work titled Cold Model Implementation of a Fractional Order Control Scheme for the Estimation of Tau. This research was developed together with Alberto Concu and Antonio De Losa, and it focuses on improving the estimation of cold model parameter using fractional order control techniques. I am presenting this talk from Ushuaia, Argentina, the third-most city in the world, often called the end of the world. Ushuaia is located at the southern tip of South America, surrounded by the Andes Mountains and the Beagle Channel. It is also known as the gateway to Antarctica, since we are about 1,000 kilometers from the Antarctic Peninsula. Before going into the details of our approach, I'd like to briefly introduce the cold model, which is one of the most common ways to describe the electrical behavior of biological tissues. When an alternating current is applied to biological tissue, its impedance varies with frequency, and this frequency gives us valuable information about the tissue's structure and composition. The cold models capture this behavior through a simple but powerful analytic expression. It is represented by this equation where each parameter has a specific physical meaning. R infinity is the resistance at very high frequencies, mainly associated with the intracellular medium. R0 is the resistance at low frequencies, includes both intra and extracellular effects. Tau represents the characteristic reaction times related to how the tissue responds to frequency changes. And alpha is the dispersion factor, which indicates how far the system deviates from ideal capacity behavior. Here you can see how tau and alpha affects the shape of the cold curve. As alpha decreases, the semicircle becomes more depressed, indicating more complex fractional dynamics in the tissue response. Our goal in this work is to apply fractional order control to improve the estimation of tau, achieving a more accurate fitting of bioimpedance data. Fractional order control builds on that idea by extending classical control theory to include non-integer derivative orders. These formulations gives us greater flexibility to represent systems with complex or distributed dynamics, such as those described by the cold model, where the response cannot be fully captured by integer order equations. The fractional nature of the controller also contributes to a smoother and more stable convergence, addressing some of the limitations found in traditional fittings methods. In previous works by our research groups, we performed a comparative analysis of different methods for fitting the call model. We observed a considerable dispersion in the estimated values of staus across methods. This motivates us to propose a fractional control systems that finds a points of convergence based on the initial values provided by one of the analysis methods. The methodology relies on experimental data from an open access databases containing electrical impedance spectroscopy measurements on time from different biological systems and application devices. 4 curve fitting methods were applied to the call model, including the methods proposed by Aylon et al., Levermer-Macquart, González Correa, Villanueva, and as well as a modified version of Aylon's methods. The fractional order control was implemented using the integer toolbox in MATLAB based on the first generation cron operator. This approach introduces a fractional dynamics terms directly into the call model, allowing a more flexible estimation of the times constant tau. Finally, model performance was evaluated using the standard error of estimates, SEE, which measures the difference between experimental and simulated impedance. Here we can see the results obtained using the conventional curve fitting methods MA, MAM, L3P, and LM before applying fractional control. The bars represent the mean standard error of estimate, SEE, for each device. As you can notice, the LM methods shows the heightened error, particularly in the storage and solar devices. This indicates that without control, the estimation of tau is less stable and more sensitive to the measurement setup and initial conditions. After applying the fractional order control, the CEE decreases significantly across all devices and all fitting methods. The improvement is especially clear in the LM methods, which initially have the largest error. This means that introducing fractional control improves the consistency of tau estimation and reduces sensitivity to experimental variability. Overall results confirm that fractional control enhances the robustness and accuracy of the fitting process. This table summarizes the main difference between conventional methods and our proposed approach. Traditional geometric fitting doesn't explicitly include tau, and it is sensitive to the electrode setup and frequency range. In contrast, our approach simulates the full call model and refines tau through fractional order control, achieving more consistent fitting across devices. The largest SEE improvement was observed in the LM method, confirming that the control loop mitigates sensitivity to initial conditions and local minima, a common issue in nonlinear optimization. Finally, a practical limitation is that our methods still depend on the initial estimate provided by classical approach. Future work will focus on extending this strategy to estimate all model parameters. Based on the SEE results, we can observe that all curve fitting methods benefited from the incorporation of fractional control in the estimation of tau. The improvement in SEE was consistent across the dates obtained with Sorartron, Zurich instruments, and Citron devices, confirming the generalizability of the proposed strategy. Also, the methods still depends on initial values. The improvement observed across all methods and dataset validates its practical applicability. As for future work, we plan to extend the fractional order control systems to estimate the complex set call model parameters and to evaluate its performance on larger experimental databases available from the bioimpedance research community. This concludes my presentation. Thank you very much for attention. I apologize for my imperfect English.
Thank you very much, Natalia. Thank you very much for your presentation. Do we have any questions here in the room? Any questions online, please? Okay, no questions. Thank you very much,
Sorry,
Natalia, for your
Sorry,
presentation.
if I can say a little comment.
Well, thank you very much, all of you, for being here. Thank you for attending this session, BIO1. And it's always my pleasure to be here with you. Thank you.
Thank you.